Hi, the lecture today is about exponential functions. I will talk about rules of exponents and explain the particular rules that we have for negative exponents and rational exponents. Then we will talk briefly about arbitrary exponents and see what does calculus have to say in that situation. After that review, we are going to talk about applications of exponential functions. Some particular applications are in population forecasting and radioactive decay. And at the end, we'll talk about a particular number that shows up in our discussion of exponential functions. Is called the number e in mathematics. That is as important as the number pi in geometry. And this is going to be a review of exponential functions for us from Precalculus. Let's get started by the following idea. In a very beginning mathematics course, you learned that if you are adding a certain number to itself certain number of times, for example, when you are adding 2 to itself 5 times, you create an abbreviation for this, and that begins to tell you about the idea of a multiplication. So you write this 2 times 5 or 5 times 2. That's one way to bring in multiplication into mathematics. Well, what if you have repeated multiplication? What if you have a number, like 2 times 2 times 2 times 2, and again one more round. If you are multiplying a number by itself certain number of times, whole number of times, you can use the exponential notation, say 2 to the power of 5. In that case, this is referred to as the base, and this number, which is number of repetition, is referred to as the exponent. So when we write something like b times b times b and so on, and then indicate number of repetition here, let's call it, say, m times. M would be a number like 2, 3, 4, etc. The abbreviation for that will be b to the power of m. Again, b acts as the base, and m acts as the exponent. A very common trend in mathematics is that once you start defining a new notation, that notation takes a life of its own, and every now and then it forces certain assumptions on you, and essentially you need to practice playing with that notation. So we have created this notation of exponential numbers here, and the question is, how do we do mathematics with them? Suppose you have, say, 2 squared plus 2 cubed. How would you perform that? Well, you know, 2 squared, by this definition, 2 times 2, that is 4. 2 cubed, well, that is 8, and then you're supposed to add them, and the answer is 12. That is not very eventful here. It's just a basic addition. Every now and then something interesting happens, and that gives rise to some new horizons and new understandings. What if I was multiplying 2 squared and 2 cubed? Well, I could go ahead and do it this way. 2 squared is 4, 2 cubed is 8, and the answer will be 4 times 8, which is 32. However, we come and open up the issue for ourselves. So remember that 2 squared meant 2 times 2, and 2 cubed means 2 times 2 times another 2. Now you're multiplying all of them together, so now you have 2 multiplied by itself 5 times, and that gives us 2 to the power of 5. Now we noticed that what happened, essentially we added up number of repetitions here, which was 2, and number of repetitions here, which was 3, and that gave us 5. So you can say 2 squared times 2 cubed is same as 2 to the power of. We just add up the exponents, and that creates a brief rule for us. So here it gives us the first rule of the exponents, which is if you have an exponential number times another exponential number, the way you can simplify this is by adding the exponents. So it becomes b to the power of n plus m. Okay, that was for addition, and not much happened over there. Here was for multiplication. Subtraction will be same as this one, and not very interesting. For example, if you have 2 squared minus 2 cubed, that would be 4 minus 8. That would be, say, minus 4. We don't have much to say about addition and subtraction here. You could do some factorization, but that's not the point right now. Next item that we are going to go and take a look at is the issue of division. What if I had 2 cubed divided by 2 to the power of 7? Okay. 2 cubed divided by 2 power of 7. 2 cubed means 2 times 2 times 2 to the power of 7. 2 times 2 times 2, and a few more of these things. I'll have 7 of them. Since they are similar in numerator and denominator, I can cancel, and now I'm left with just 1 divided by 4 2's are left here, which is 2 to the power of 4. I can abbreviate the whole work and say I had 3 2's here and 7 in the denominator. 3 of these cancel out, and one way to arrive at the same answer would be to say 2 cubed over 2 to the power of 7 is 1 over 2 to the power of, no, 7. I had 7 2's, 3 of them got cancelled out, and I'm left with just 4 2's. So the answer is 1 over 2 to the power of 4. Let's look at the same thing upside down. Suppose I have 2 to the power of 7 divided by 2 cubed. Same story as before. This is repeated 7 times, and this is repeated 3 times. And I can cancel 3 of these 2's in the numerator and denominator, and the answer will be, I have 4 2's left. And in this case, I can write the answer as 2 to the power of 7 over 2 cubed as 2 to the power of, I can subtract the exponents, and now I get 2 to the power of 4. Same answer as I got over here. Now, it would be interesting if we could do both of these with the same rule. As you notice here, I am keeping the number with the larger exponent in the denominator and subtracting the exponent of numerator from that. In this case, the exponent in the numerator was the higher one. I subtracted the denominator's exponent from that. Can we combine these things into the same rule? Can I use this approach here or this approach over there? Let's go ahead and do it like that. Suppose I have 2 cubed over 2 to the power of 7, and I want to perform it in this style. I would say 2 to the power of 3 minus 7. Well, now the answer is minus 4. What's the problem now? The problem is at the very beginning, when we were defining this operation, this number of times had to be whole number of positive whole number of times. It does not make sense to say I'm multiplying a number by itself minus 4 times. So here, this answer that we are writing does not make sense according to our original definition. In order to make life easier for ourselves, we come and say, to be able to perform this operation quickly, we might as well go ahead and define 2 to the power of minus 4 to be what we saw here. So here's a definition 2 to the power of minus 4 is same as 1 over 2 to the power of 4. So once again, negative exponent does not make sense based on original definition. Now, for sake of convenience and uniform treatment, our operations and calculations, we come and define this. So in general, we have the following definition, that a number raised to a negative exponent, let's write the negative exponent as negative n, with n being positive, same as 1 over that number raised to the positive exponent. So this is the rule that was forced upon us when we wanted to have a uniform treatment of both of these two fractions. While we are here, we might as well also write the second rule of operating with the exponents. So if I have b to power of m divided by b to power of n, I'll write that as b to power of m minus n. Now we have talked about addition, subtraction, multiplication, and division. Next item to talk about is exponentiation of an exponential number. Suppose I have 2 cubed. That's an exponential number, and I want to square it. What does that mean? We want to understand what it means and then go ahead, learn the rules, and be quick about it. We have two kind of exponentiations. This exponentiation here means 2 cubed has to be multiplied by itself twice. So far that's what it means. Now I have 2 repeated here 3 times, and then again another 3 times, so there is going to be a total of 6 times, so 2 to the power of 6. Where did 6 come from? 3 plus 3 is 6. Let's try this again. If I have 2 cubed to the power of 5, that means 2 cubed times another 2 cubed times another 2 cubed, and so on. Now I have to add up all these exponents. I'm adding 3 to itself 5 times, and the shorthand for that is just 3 times 5, or 15. So the answer is 2 to the power of 15. What we see from all of this is that b to power of m as an entity, if that is raised to power of n, we get b to power of m times n. We multiply the old and new exponents. Now that gives rise to an interesting observation, which is the following. What is meant by a rational exponent? Suppose I have 2 to the power of 1/3. What is the meaning of that? Well, I'm sure you have seen it in your Algebra 1 or 2 classes, so you have a ready answer for this, but I want to attract your attention to the following fact, that it does not make sense based on this original definition to talk about 2 raised to the power of 1/3, because you cannot multiply a number by itself 1/3 times. You either multiply twice or 3 times or 5 times. You cannot multiply by itself a fractional number of times, just in the same way that you could not multiply it by itself a negative number of times. So how do we make sense of that? The clue comes from this rule we just learned here. This rule for the this rule that we learned for the exponents. This one says that if I have an expression like 2 to the power of 1/3, if I take it and then cube it, multiply by itself 3 times, if this rule wants to be valid all the time, then the answer has to be what? 2 to the power of 3 times 1/3 is just 1. 2 to the power of 1 is just 2. So 2 to the power of 1/3 is an entity that if you cube it, you get 2. So what's the definition of that entity? The entity that if you cube it, you get 2 is shown in elementary mathematics as the cube root of 2. So what we have now is another definition that a number raised to a fractional exponent is 1 divided by number is in fact that particular root of that base number. Let's write this definition like this. If I have b raised to power of 1 over n, by that I mean the nth root of b, assuming that that root exists, and we are staying away from taking the, say, square root of a negative number and such problems. The definition of a number raised to 1 over n is same as nth root of that particular number. So that rule is brought to us as an extension of this double exponent rule. Similarly, b raised to power of a fraction, arbitrary fraction, with a number on the numerator, another number on the denominator. This is going to be the mth power of this, which you can write in one of two ways. Either you can write it as nth root of b to power of m, or you can write it as nth root of b, and after you're done with the root, you can raise it to power of m. While we are here, let's mention another definition that I'm sure you're all familiar with, and that is b to power of 0. That you know what the number to power of 0 is. What's a number to power of 0? That's just 1. Why is that an issue here? Let me just mention one more time. It does not make sense in this context to say I'm multiplying a number by itself 0 times. If it's 0 times, you're not writing anything here at all. So what number are you referring to then? So it does not make sense based on that. So what's the reason that we come and define b to power of 0 to be 1? Here is a justification. There has to be a reason we are making these peculiar definitions. Suppose I had b squared divided by b squared. Well, these are the same numbers. If you divide them, you're supposed to get 1. On the other hand, what if I want to apply rules of exponents? Rules of exponents tell me I can subtract the two exponents from each other. If I do that, I get b to power of 0. For our answers, following the rules to be automatically same as something we know to be correct, we are forced to define b to power of 0 to be 1. So observation that we have after looking at this answer is that it makes sense to define b to power of 0 to be 1 so that our operations go through smoothly. So these were some basic rules of exponentiation that you see in algebra 1 or 2. Next, we come to something a lot more advanced than all of these things. So at a calculus level, we are facing questions such as this. What is the meaning of b raised to power of, say, square root of 2? So far we have dealt with the negative exponents, fractional exponents, 0 exponents. What if the exponent isn't any one of those? What would be the meaning of that? Or suppose I have, say, 5 raised to power of square root of 3. What is the meaning of that? Well, so question is, what is the meaning of a full understanding of this requires a concept of limit that we are going to talk about in a week or so, but right now we're just getting our feet wet with some advanced concepts. The way to understand these things is by approximation and by limits. So what we require here is some understanding of approximation and limit. What does that mean? Well, this radical 2 here is a strange number for us to deal with. So I might go ahead and approximate square root of 2. What's an approximation of square root of 2? Here's a good approximation, 1.4. You can use your calculator, or from somewhere you find out square root of 2 is approximately 1.4. So it makes sense for us to replace that square root of 2 by an approximation and perhaps be satisfied with that. So I might think about b raised to power of square root of 2 is approximately same as b raised to power of 1.4. Well, what is b to power of 1.4? We hadn't written decimal exponent before, but that's not a major headache. B to power of 1.4 is same as, I can write 1.4 as 14 over 10. In that one I can write as 10th root of b to power of 14. So one approximation for this is given by this expression here. What if I want a better approximation? Well, if I want a better approximation, I have to pay more. Pay more, I come here and approximate square root of 2 a little bit better. Let's say we borrow one more digit from our calculator, so 1.41. Then b to the power of radical 2 is approximately b to power of 1.41, which is equal to, well, 1.41 is 141 divided by 100, and that means you're taking 100th root of b raised to power of 141. That looks like a daunting task to do, but we are not going after actually calculating any such thing. We are just getting to the concept of what does it mean to raise a number to a number that is not rational. They call them irrational numbers. Well, what if you want better answers? Well, better answers comes when you have more digits here. That brings you to the idea of approximation. You're approximating radical 2 by this decimal number, and you're using that in place of the exponent. What's the concept of limit? Well, as we go down the list of this approximation, we are getting closer and closer to ultimate destination, to the final reality, which is that square root of 2 itself. So concept of limit is the concept of tracking all of these approximate answers and finding out where they are headed to. So that's a concept that we are going to follow later on, and right now I just wanted to mention that as we said at the very beginning, as soon as you start defining a notation in mathematics, it takes a life of its own, and all sorts of problems start to show their faces, and then we have to be aware of them and have a way of resolving all those issues. Next issue that I want to talk about very briefly, some other rules of exponents that you're familiar with. So far we have had only one base. What if I have two bases, like one base and then another base multiplied with each other and then raised to an exponent? Go ahead and justify it to yourself that based on what we have learned so far, it's the same as the first number raised to that exponent times the second number raised to that exponent. Okay, it's a good place for you to pause this video and try to justify to yourself, why is this same as that? Here's an explanation. Suppose I had AP cubed. Well, that means AB times another AB times another AB. Now I might as well put all the A's next to each other and all the B's next to each other, and now I have A cubed, B cubed. So the reason that you can do this is partly explained here. To talk about this, what happened here in general, we say we have two operations that we have here. One of them is this multiplication, and the other one is this exponentiation. One operation and a second operation. On the left, you multiply first and exponentiate second. On the right, you exponentiate first and multiply second. So you have changed the order. We say these two operations commute with each other. Here you are exponentiating first, multiplying later. Here multiplying first, exponentiating later. That brings you to the idea of commutativity of two operations. That's a fancy title, but I'm sure you're familiar with the operation itself. Let's go after the same thing. For division, you can do this exactly by the same logic. You can perform this. Again, you have here exponentiation and division, and here you are exchanging the two operations. One thing to pay attention to here is that you cannot do that with addition or subtraction. A plus b to power of n typically has nothing to do with a to power of n plus b to power of n. You cannot commute these two. So for example, a plus b squared is not same as a squared plus b squared. What is missing on the right hand side? Do you have the answer ready? Yeah, it's missing a 2ab, and if you're cubing it, it's missing a lot more. So a plus b to power of n is a complicated thing. You might have seen it in the topic of binomial theorem. Right now we are not getting into that, just a warning. So every now and then you see a warning sign in this lecture material as a common error to be avoided. Okay, we had these other rules of exponentiation. Let me mention a couple of other items before we move on to more advanced issues. The first item is, what if I had a ladder of exponents, 2 to the power of 3 to power of 2? What is meant by that? Well, the issue is that you can read that one of two ways. Here we had the ladder of exponents too, but there was a parenthesis, and we said the resolution was that you are multiplying these two exponents to get a net exponents. In absence of a parenthesis, what this means is that you are resolving the issue from the top and working your way to the bottom. That is, you are supposed to take 3 and square it, and then use that as the exponent. So the answer here is 2 to the power of 9. It is not 2 times 3, rather it is 3 squared. So that is one item to be careful about. So in absence of a parenthesis, if you have a ladder of exponent, you work your way from top to bottom. Second issue, what if I have a number such as -2, well, let me change this to something else. Yes, minus say 4 squared. What is that? Again, we have two operations here. One is this act of taking negative of a number, negation. Another one is the exponentiation. Which one is going to happen first? You learn from Algebra 1 that exponentiation is at the top of the food chain. That's one that gets to be happening first. So 4 is squared. After that is performed, you are calculating the negative of that, so you get -16. As opposed to what? As opposed to having a parenthesis, if I have -4 in the parenthesis squared, the minus 4 times another minus 4, it is 16. So exponentiation happens before multiplication by negative sign. I have exponentiation first, so-called rules of operation, and then I have multiplication or division, then I have addition and subtraction, and then there are other tiebreakers that we needed to be aware of, like in exponentiation. If you have a ladder of them, you work from top to bottom. If you have several multiplication and division, you work from left to right. Addition, subtraction, again left to right. And of course the trump card in all of these things is parentheses. Parentheses goes first in any of these calculations. So those were some of the basic rules of exponentiations. Of course you have to be familiar with this so that you absorb the review quickly. Next issue that we are going to talk about is the graph of exponential functions. Well, suppose I want to graph y is equal to 2 to the power of x. We are going to look at this function in much more detail later on. Right now, again, this is a warm-up exercise at the beginning of the semester. What does it mean to graph this function, and what are the properties of this graph? First time around that you come across a function that is perhaps unfamiliar to you, the best thing to do is to make a table. So you make a table for the variables involved. You just have an x and a y, horizontal or vertical table, and then you go choose some numbers for one of these variables and find the other one, however it's convenient to you. At the very beginning there is really no rule as to what is it that we have to go and look at, so this is rather random. For x we choose some convenient number. It's just based on the convenience that, like, we go after the most familiar numbers we know about in life: 0, 1, 2, 3, -1, -2, etc. As you mature in mathematics, you will learn that one main issue is how do I choose the x's intelligently so that I get a full story as opposed to some random view. Right now we just pick these numbers and plug here and see what we get. 2 to the power of 0, we learn that that is 1. 2 to the power of 1 is 2. 2 squared is 4. 2 cubed is 8. Negative exponent, we learned that that gives us a fraction, 1/2, quarter. 2 to the power of -3 is 1/8. So for example, where did this come from? 2 to the power of -3 to raise to this x value gives me this y value. What do I do next? Next is to draw a coordinate system. So here is a quickly drawn coordinate system, x and y axis. On this xy axis I go and choose some reasonable size units. For example, maybe this is a good 1, 2, 3, and here's 1, 2, 3, 4, 5, 6, 7, 8. Here's -1, -2, -3. Let's start at -3. I'm at 1/8, very close to the x-axis. -2, I'm a little bit higher up. At -1, and I'm at 1/2. At 0, I'm 1. At 1, I'm at 2. At 2, I'm at 4. And at 3, I have 8. So now if I go ahead and connect these points, But why do we connect them? Why not just leave them alone? That's going to open up a whole set of issues in mathematics. By connecting, what we mean is that if I had the patience to go ahead and fill up this table with a lot more numbers, like between 0 and 1, there are lots of numbers, like 0.5. And take 2, raise it to the power of 0.5. That is going to give me, use my calculator or something, 1.4 and so on. That means that at 0.5, I expect to get 1.4. And that's going to be one dot here. If I take 0.6, 0.7, and so on, and patiently find lots of points, then gradually the space between these orange dots is going to fill up. And when it fills up, I'm going to get a curve that is going to have such an appearance. So finding points and connecting them is called point plotting, is the most rudimentary way of graphing a function. We are going to talk about graphing functions much more detail later on, but right now that's what we are going to do. Find several points and connect them and hope that what we have is a reasonable approximation to the actual fact and the truth. So here we have a graph of y is equal to 2 to the power of x. What you want to do is to get yourself used to sitting down and graphing functions. It's a rather tedious task. It's kind of laborious, but that's the only way you actually get a feeling for the mathematics and operation and learning how to correct your own mistakes and so on and so forth. Graphing a function just requires patience right now, nothing else, just patience. So just sit down, make your table, find the x and y's, and plot them, and expect a reasonable looking picture. Here are some other functions we might like to graph. 2 to the power of minus x. Well, let's quickly go ahead and do this one. Here's x, here's y. Let's take a look at the same set of numbers. I'm afraid that you will get hooked to these numbers and thinking that somehow these are some holy numbers and such. They are just convenient numbers to work with, and later on you have to wean yourselves off of these things. So if x is minus 3 and I use it here, minus 3 makes plus 3, and 2 cubed here will be 8, and this one will be 4, and 2, and a 1 to the power of minus 1 is a half, a quarter, and an eighth. So all that happened here is that compared to this other table, our answers coming out in reverse. The numbers that were used to show up on the right now showing up on the left. The left and right exchanged their spots. 8 came here, 1/8 went over there. What does that do to the picture? That's one topic you learn in Precalculus, which I hope you have taken. If you change x to minus x, that has the net effect of flipping your picture. This was going up in this style, taking right side to the left and left side to the right. It's going to give us a picture like this. The net picture is going to appear Of course, it's best to have a graph paper and do this thing carefully so that you get a decent looking picture. Of course, that's going to take a little bit more time. So make sure you do practice these graphing questions, as many of them as you do. You'll be doing yourself a favor. Once again, it's not the most fun thing to do in the world, but you need to exercise some patience and be able to get pictures quickly and accurately. Okay, we promised that we'll talk about a couple of applications in this topic. Applications of one of the very famous applications of exponential numbers is to population forecasting. suppose you are growing rabbits in a farm, and then under certain ideal circumstances you say that if there is enough room and enough food and such, the population of rabbit can double every say 6 months. Okay, and suppose you start with the population. Starting values are traditionally in sciences are shown by a letter followed with a little zero underneath it. PO or P0 is starting population. Suppose your starting population on the farm is 100. Well, and natural cycles are on a 6-month basis. After 6 months, I want to know how much will be in the pen. So population at 6 months. So P stands for population, and then I want to indicate the time at which I'm looking at the farm, see what's going on. It's going to double, so it was 100, now it's going to be 100 times 2. Now we want a notation that's a little bit more compact than this. That's a standard game in mathematics, to make things as compact as possible. So either we refer to it as 6 just month, or perhaps using a unit of years, I might write it as P. This is a half of a year. So this is a population at half year is 100 times 2. Well, what's the population if I wait 1 year? 1 year means, so these are measured in unit of years, and we typically don't write the unit. Well, it's going to double again, is that right? It was 100 times 2, and then times 2 again. Now, what if I wait 1.5 years? 18 months. So whatever I had is going to double again. Well, suppose I want to let it go for say 6 years. What's going to happen? How many times would I multiply by 2? Of course, it has to do with how many periods there's going to be. In 6 years, every year is 2 periods of 6 months, so that's going to have 12 doublings. So I'm going to have many of these 2's. How many of them? 12 times. Why 12 times? Because 6 years has 12 6-month periods. So what's the shorthand for this? Shorthand for this is 100 times 2 to the power of 12. That's about 4,000 itself. Times that makes 400,000. Assuming that you are not doing anything with your rabbits other than just letting them grow and willing to have rooms for them and have food and so on and so forth, they do grow up and perhaps run you out of the farm. So that is our formula, P at time t. Let's see if we can write a formula for it. That's 100 times 2. Now, how many periods is there going to be? Suppose this is t years. It was 1.5. I had 3 periods. 6. I had 12 periods. T years. How many periods is that going to be? So every year is 2 periods, and t years is going to make it 2t periods. Writing it in a little bit more fancy and advanced style, the meaning of this 100 was P0, initial population. 2 came out of statement of the problem, that we are measuring things by how long it takes for it to double. How about this other 2? This is how many periods are there in 1 year? What if I had said the rabbits are doubling every 3 months? What if rabbits double every 3 months? What would be the formula there? Well, everything will be same as before. Initial population. We are talking about doubling. The question is, how many doubling periods are there? If the rabbits double every 3 months, well, in every year there are going to be 4 doubling periods. Is that right? A year is 12 months. Every 3 months the rabbits are doubling. So that's going to happen 4 times in a year. That's going to be 4 times t. In general, if it takes, I want to translate this thing in a general mathematical notation. If it takes d years to double, what does that mean, d years to double? Like this. How many years does it take for the rabbits to double? 3 months is, that's a quarter of a year. So d is 0.25. How about here? What is d in this case? D, 6 months, is half a year. Here d was 0.25. So if it takes 0.25 of a year to double, in a whole year we are going to have 4 doubling periods. What about in general? In general, you take initial population times 2. If you are waiting t years, you want to know in t years how many doubling periods there are. You have to take t and divide it by d. So d is the length of time it takes for your population to double. T is the number of years you wait. P0 is the original population, and this number 2 came out of original statement of the problem that somehow you're interested in doubling periods. If you are interested in tripling, this would have been a 3. So here we justified one place where exponential functions get to be used on a regular basis. Population forecasting and population analysis, based on very simplistic assumption, we arrived at this formula. The other side of the coin, very similar to this, is the idea of radioactive decay. So the other application we have in mind is radioactive decay. What happens in radioactive decay? You might have a substance. Every now and then you hear about this thing in the news. Somebody swallows some radioactive substance to pay for it later on. So radioactive decay, some material in nature have a tendency of disintegrating. Some heavy metals have this property that you might have a container full of this, and you come back in a certain after a certain length of time, you come and look at this, you see that half of that substance is gone or turned to something else, and only half of it is still there. And then you go and come back after the same length of time, you see the same thing has happened, that again, out of this substance, half of it is there and the other half has either evaporated or converted to some other substance. The length of time it takes for half of a substance to disappear, this is called half-life. Okay, so sometimes you hear politicians debating about how to bury radioactive substances, and they say that the life of this substance in 10,000 years. What does it mean, the life of it is 10,000 years? It means if you bury that substance in somebody's backyard, come back 10,000 years later, half of it is still there, and the other half has disintegrated to something else, which itself might disintegrate or do something else. Half-life is the length of time it takes for something to become half of what it was. Nice thing about half-life is that it's a constant. If you wait another half-life, whatever there was, that is going to be cut by a factor of 2 one more time. To explain this thing, let's take an example. Suppose we have a substance, and at the beginning the quantity that we have, so quantity we show by Q, Q0 is going to show us a quantity at time 0. This is like at the beginning of some experiment. Suppose we have 100 grams of this substance sitting around. Suppose the half-life of this substance is, say, 2 minutes. So if I come back and look at this after 2 minutes, so we might show this about Q at time 2. After 2 minutes, the quantity at time 2 minutes, if this is 2 minutes, half of this is still there. Just to make sure that I'm not confusing you, let me change something. Suppose this is 3 minutes, so that my numbers do not collide with each other. So I changed my mind, made it to 3 minutes. So if I wait 3 minutes, so this we made this to be 3 minutes. If I wait 3 minutes, how much of it is still there? Half of it is still there. What if I wait another 3 minutes? So by now I have waited 6 minutes. So half of it was left first round. Another half of a half is going to be left on the next round. So after 6 minutes, what happens is that I multiply by half again. So by now a quarter of it is left. If I wait 9 minutes, what's going to happen? Well, the game is going to repeat itself, and I'll be down to 1/8 of what I had at the very beginning. So what if I wait t minutes? How many of these multiplications would I have? Can you pause for a moment and give me a rule that can tell me how to figure out how many times to multiply by half? Here is your clue. 3 minutes, 1 time. 6 minutes, twice. 9 minutes, 3 times. If it is t minutes, how many of these things should I do? Of course, the number that you have here is 1/3 of how many times, how many minutes you have waited. So this is t over 3 times number of times you are multiplying. So how can I abbreviate this whole thing? I can abbreviate it as Q of t is equal to 100 times 1/2 to the power of t over 3. We have learned all sorts of mathematical ways of compressing this. Instead of 1/2, I can write 2 to the power of -1. Instead of having 2 exponents, I can compress it just into 1 exponent, minus t over 3. radioactive decay problems are characterized by the presence of this negative sign. It means things are dying away, disappearing. This is the half-life in a unit that you're measuring in the numerator. This number 2 came into the problem because we were partial to half-life. If we were, for some reason, we were interested in 1/5 of a life, this would have been a 5. What is this? 100, that is the initial substance. So Q in general is Q at time 0 times, if you are interested in half-life issue, this will be a 2 fixture here, divide to the power of how many minutes you are waiting, divided by, well, what was this 3? That was half-life. Let's show it by the letter H. So H is the half-life of the substance you are investigating. So once again, original amount at time t. This was the half-life issue. Half-life itself is shown by the number in denominator h here. T is the length of time that has passed, and minus indicates that things are actually decaying. Okay, we learned about exponential functions and its applications. Now we are going to say a few words about the number e. There is a number that comes up in mathematics in a variety of applications that is as famous as the number pi is. And e is a shorthand for this particular number. It has a value 2.71828, and so on it goes. You can get the digits of that to millions and billions of decimal places. It's not a rational number. You cannot write it as a ratio. Is not the square root of something. It is truly a complicated number. This number comes up naturally in a variety of applications. So later on in the course we are going to explain, for example, where it could come up in the context of simple interest rate calculations. But it is all over the place, and right now we're just getting used to working with it. This number comes up in one place in mathematics as the base of the exponential function e to the power of x. So e to the power of x is a shorthand for this number. We don't want to write this number every time, so we abbreviate it to e. Your calculator has a button with this e to the power of x written on it. We want to get some understanding of it. Right now, basic thing to understand is perhaps what's a graph of y is equal to e to the power of x. Well, we just practiced what the graph of 2 to the power of x look like. Let's just quickly go over that. 2 to the power of x, you remember it looks look like something like this. That was a friendlier number, 2 to the power of x. We could say 2 to the power of 0 is 1, 2 to the power of 1 is 2, and so on. Well, what if I change my base to 3? 3 to the power of x, I'll leave it to you to go and figure out that 3 to the power of x looks like something like this. 3 to the power of x. Well, if you try to figure out 4 to the power of x, it is going to ascend even faster. Given the fact that e is somewhere between 2 and 3, we expect the graph of e to the x to be also somewhere between these two graphs. So graph of this function is going to be approximately looking something like this. Later on, so this is e to the x. We are going to single out e to the x from this bunch of functions that are here by a peculiar property. This is the function that starts off at 45 degrees. That is this. starting angle of this function is going to be 45 degrees for us. So halfway between x and y axis, that's where e to the x takes off. That's one characteristic of it. In comparison, the angle at which 2 to the x starts is not a very well known angle. Neither is that the case for 3 to the x. So e to the x, this strange looking number, has one justification for it, which is this graph starts at essentially northeasterly direction at 45 degrees and takes off and goes. But of course we need a lot more justification for its importance than just that. Okay, I trusted that you go ahead and do a lot of graphing from problems of this section. Again, all it takes is patience and a calculator, and that is going to be enough for graphing of these problems. You go ahead and do the problems of this section. Good luck and God bless.